Now, we continue the lecture of engineering plastics following the first part of engineering plastic. Let us start with polycarbonate, so-called PC. Polycarbonate has been synthesized by two different methods. The first method is interfacial reactions. The other method is melt reactions. In the interfacial reactions, bisphenol A is reacted with phosgens to produce polycarbonate with the removal of hydrogen chloride. The interfacial reaction is the interfacial reactions takes place at the interface between aqueous phase, that is, BPA is dissolved in sodium hydroxide aqueous solution, and organic phase, that is, phosgen is dissolved in chlorinated solvent. In these interfacial reactions, amine catalyst has been used, more specifically trialkyl amine or pyridines, as the catalyst to trap hydrogen chloride as byproduct. The melt reaction is a condensation reaction between bisphenol A and diphenyl carbonate here. So with removal of a phenol here, in these melt reactions, catalysis is not necessary. And therefore, just the continuous stirring and reduced pressure for effective removal of a phenol are required. The melt reaction is commercially available, and the industries, most of industry use the melt reactions. So particularly, BPA-based polycarbonate has many good properties, such as high glass transition temperatures, 145 degrees centigrade. That is much higher than glass transition temperatures of PET or PBT. So PC has excellent impact strength, excellent transparencies, flame retardancies, and excellent thermal stability, high tensile modulus, excellent stress relaxations, and PC shows good moisture resistance. And therefore, the PC has been used for many applications, such as automotive lighting here, this cover for automotive headlight, and this is bottles for mineral acid. And here's the architectural looping is made of PC. Also, this cover for high intensity LED lighting, and this CD is made of PC. And also, PC has been applied for medical devices such as a goggle and is the test tube, etc. So in order to improve heat resistance of polycarbonate, so we may replace bisphenol A with more bulky or sterically hindered monomers. Now, since R is bisphenol A, that is BPA-based polycarbonate, which is widely used as most common. And R is replaced by 1. 1 is a tetramethyl bisphenol A. And then the glass transition temperature is 207 degrees centigrade, which is higher than the BPA-based polycarbonate, that is 145 degrees centigrade. Now, so R is replaced by 2. This is tetramethyl bisphenol S. And then the glass transition temperature of the PC is 260 degrees centigrade, which is much higher than BPA-based polycarbonate TZ. And particularly now, this monomer is replace R, and then the carbonate shows very high glass transition temperatures of 290 degrees centigrade. Now, as I mentioned just before, polycarbonate has excellent impact strength. However, in order to further increase the impact strength of polycarbonate, so you may use polydimethyl siloxanes. So polydimethyl siloxane is dimethyl siloxane. This is polydimethyl siloxane. It is recognized for its stability and flexibility, and is commonly used in medical applications. And there are two methods to improve impact strength of polycarbonate. One method is simple blending of polycarbonate and polydimethyl siloxanes. Simple polydimethylsiloxane polycarbonate blends have been known to show excellent impact strength. Another method to improve impact strength of polycarbonate is to use black copolymerization method. The black copolymers of PC and the PDMS, polydimethylsiloxanes, are synthesized from suitably handicapped polydimethylsiloxane precursors. Indeed, savvy, innovative plastics company commercialized the black copolymer of polycarbonate and polydimethylsiloxane under the trade name of Lexan EXL. This Lexan EXL is known to show superior impact strength. Now let's move on ketone-based thermoplastics. Polyaryl ether ketones is simplified by PAEKs, are highly aromatic and most semi-crystalline thermoplastics. Several examples of ketone-based thermoplastics are PEEK, PEEK, PEEKEK, etc. Now, so when you look at this figure, this chemical structure is named as ether-ether ketone. Therefore, this polymer is named as polyether-ether ketones, which is abbreviated by PEEK. Now, when you look at this chemical structure, ether-ether ketones, therefore, this polymer is named as polyether-ether ketone, that is abbreviated by PEEK, just we call the PEEK. What about these chemical structures? Ether-ether ketone, and therefore this polymer is abbreviated by PEEKEK. Now this is a simple one, polyether ketones, PEK, just a pack, right? So ether-ether ketone, so PEEKK, ether ketone, so that this is named as PEKEKK. Here's PEKK, PEKKK, right? Among these, polyether ketone here are called PEEK or PEEK, PEK, is most widely used, has been commercialized. So let's look at the synthesis of polyether ketone, PEEK. This PEEK has been synthesized by reacting difluorobenzophenols with hydroquinones in the presence of alkali carbonate as a catalyst in a polar apoptic solvent. And this is a chemical structure of polyether ketone here, right? So sometimes we may use new catalysts, for example, N-alkyl, N', dialkyl aminopyridine. When you use this new catalyst, so we may achieve not only high molecular weight, but also high reaction rate. So this table compares the thermal properties of polyether ketones. This is a polyether ketone, so that is simplified by PEK, ether ketone, PEK, ether ketone, PEKK, this ether ketones, PEKK. Here's it by phenyl unity. Here's we can name of these polymers. Now when you compare the thermal properties, more specifically glass transition temperatures and melting temperatures, you may realize that this ether content here is 50%. What about this one? The ether content is 66%. And what about this? This is 33% ether content. As the ether content increases, the thermal property will be decreases. This is the highest ether content as the lowest melting temperatures. And this is the lowest ether content is the highest melting temperature. So the PEEK has been used for many applications, such as aerospace and applications. This PEK replaces metals in the airplanes. Also, this PEK can be used for automotive parts, gears, seals, sporting rings, anti-lock braking systems like this, and a vacuum pump. And also, the PEK can be used for electronic devices, switches, circuit board, and connectors, sensors, audio speakers. Particularly, PEK is biocompatible, and therefore PEK can be used for medical applications here. For example, spinal devices orthopedic devices, trauma devices, neural carriers, pharmaceutical devices, etc. Now let's move on to polyether sulfone. This is also very important engineering plastics. PES, polyether sulfone, can be produced by using weak base such as alkali metal carbon as a catalyst in dipolar aprotic solvents such as dimethyl sulfoxide, and N-methyl pyridone, and dimethyl acetamide. This dihydroxy diphenyl sulfone is reacted with dichloro diphenyl sulfone. So in the presence of alkali metal carbonate as a catalyst in an aprotic solvent to produce polyether sulfone. This is polyether sulfones with the removal of alkaline chloride and water and carbon dioxide. Another method to synthesize polyether sulfone is that dichlorosulfone diphenyl ether reacted with diphenyl ether. So in the presence of a catalyst with the removal of hydrogen chloride to produce polyether sulfone. So there are several types of polyaryl ether sulfone. This is just we mentioned earlier, polyether sulfone, ether sulfones. This polysulfone, so-called PSU, has been synthesized by reacting. This is bisphenol A reacted with dichloro diphenyl sulfone. Or polyphenylene sulfone has been synthesized by reactions dihydroxy diphenyl reacted with dichloro diphenyl sulfones. Now, when you compare these three types of polyaryl ether sulfones, the glass transition temperature PS is high, 220 degrees centigrade. So, however, if you look at this property of PSU, polysulfones, the glass transition temperature is a little lower than this glass transition temperature PS. However, transparency of PSU is higher than polyether sulfones. So transparency is sometimes very important for practical applications. So polyaryl ether sulfones are generally amorphous, and the color of polyaryl ether sulfones are slightly yellows. In other words, the plastics show amber hue, and the most of polyaryl ether sulfones are soluble in N-methyl pyridones and dimethyl acetamide and pyridine and anilines. However, the polyaryl ether sulfones have many good properties. And they are transparent and rigid and tough. The glass transition temperature is very high, particularly the glass transition temperature PS is 220 degrees centigrade, which is much higher than glass transition temperature of PET and PBT polyamides. And they also show long-term thermal oxidative endurance and very high temperature thermal stability. And they also show low thermal expansion coefficient. In other words, mold shrinkage is relatively low. And they exhibit resistance to hydrolysis and resistance against the acidic and basic attack. And they also show good electrical insulating properties. And they are inherently flame retardancies. They show resistance to oils and greases and excellent resistance to hydrogen bonding solvent such as alcohols, glycols, and aliphatic amines. And therefore, polyether sulfones has many applications. For example, they can be used for food service and food processing. Coffee pots, you may use every day. Coffee maker components and microwavable bowls are made of PS, right? And they can be used for plumbing components, such as faucet waterways, mixing valves, hot water heater components, distribution manifolds, and plumbing fits. Particularly, they can be used for membranes, for gas separation membranes, reverse osmosis and forward osmosis, nanofiltrations and ultrafiltrations, and macrofiltrations. So most of the separation membranes can be used is made of polyether sulfones. So they also can be applied for the electrical and electronic components, such as high voltage transformer magnetic wires here, and printed circuit board and circuit breaker components, and they can be used for structural forms and high performance coating. Now let's move on alkyl substituted polyphenylene oxide, simply called PPO. Sometimes we may use polyphenylene ether that is abbreviated by PPE. So PPE is equal to PPO anyway. This PPO is synthesized by reaction of 2-methyl phenol with oxygens in the presence of catalyst copper chloride in the pyridine solutions. This is the polyphenylene oxide. So this PPO is really the first example of polymerization by oxidative coupling reactions using oxygen as an oxidizing agent. So this figure shows the polymerization mechanism of the dimethyl phenol by oxidative coupling. This is the monomer, it says dimethyl phenol, 2,6-dimethyl phenol. This monomer is oxidized by oxygens to produce the monomer radical. So dimethyl phenol radical. This radical attack this monomer to produce intermediate and finally to give dimer. And this dimer is oxidized to produce dimer radical. This dimer radical attacked monomer radical to produce this intermediate and then finally to give tetramer. This dimer is oxidized again, is dimer radicals. This dimer radical attack the dimer and to produce this intermediate finally to the monomer radical and trimer radicals. And this reaction proceeds to make high molecular weight, the polyphenylene oxide. So this PPO has many good properties. The glass transition temperature is very high, it's 280 degrees centigrade. And this polymer is crystalline, and therefore the melting point is 257 degrees centigrade. This PPO is soluble in hydrogenated and aromatic solvent. And PPO shows excellent electrical insulating properties, the exceptionally dimensional stabilities, and they exhibit low thermal expansion, and therefore mold shrinkage is very low. They show low water absorptions, and very good hydraulic stabilities, and good chemical resistance, and they show self-extinguishing. However, the critical disadvantage of PPO is very expensive. And therefore, we need to blend with the cheaper plastics to reduce the cost of plastics. So that PPO has been used in the blender forms rather than PPO alone. So there are 3 types of PPO-based polymer blends. The first type of PPO-based polymer blend is PPO is blended with styrenic materials, particularly high-impact polystyrenes. That blend is called the styrenic PPOs. And PPO can be blended with polyamides. So the blend is named polyamide PPOs. Also, PPO can be blended with PBT and PPS. So among these, styrenic PPOs has been commercialized and most widely used. So the PPO is miscible with the polystyrenes, and therefore the blend shows uniform morphologies. And styrenic PPOs have good dimensional stabilities, and therefore mold shrinkage is very low. And they show low water absorptions, and therefore pre-drying is not necessary. And they show excellent resistance to hydrolysis. And the styrenic PPOs show very good dielectrical properties of a wide range of temperatures. And they show heat distortion temperatures as high as 160 degrees centigrade. Particularly, styrenic PPOs are cheaper than other super engineering plastics such as polycarbonate, and polyphenylene sulfide, and polyether sulfones. And they also show good melt thermal stability. So this PPO or PPO blends has been used for many applications such as automotive industries. For example, instrumental panels looks like this one, and steering column claddings, and central consoles, loudspeaker housings, nozzles, etc. They can be used for electrical industries, such as cable connectors, bulb socket and switch cabinets, and fuse boxes and housings for small motors, looks like this one, and the transformers and protective circuits. And they can be used for radio and television, such as coil formers, picture tube deflection yokes, insert card mountings, etc. Now, so we focus on polyphenylene sulfide, so-called PPS. Dichlorobenzene is reacted with sodium sulfide to produce polyphenylene sulfide as of simple reactions with removal of sodium chloride. So PP has many good properties. PPS has highly crystalline. The melting point is about 285 to 295 degrees centigrade. The glass transition temperature of PPS is in the range of 85 to 150 degrees centigrade. And PPS shows good heat resistance and excellent flame retardance resistance. The limiting oxygen index of PPS is 53. This 53 means that when the oxygen composition in the air is higher than 53%, and then the plastics just start to burn. In other words, as you know, the oxygen content in the normal air is 20%, and therefore PPS does not burn under the normal air conditions. In other words, the higher the limiting oxygen index, the better the flame resistance. So PPS shows an excellent chemical resistance and electrical insulating characteristics, and the tensile properties of PPS is comparable to other engineering plastics, and PPS is easily filled by glass fiber and carbon fibers, and therefore PPS can be used in the form of a composite rather than PPS alone. Composites are really of a commercial interest. And there are three types of composite. The first example, the composite is glass fiber reinforced plastics composite, in which the 30 and 40% glass fibers are reinforced in PPS. And glass fibers, and particularly mineral reinforced composite, that composite shows the highest temperature ratings, good arc, and tracking resistance. And third, the most important, the composite is carbon fiber reinforced composite. These composites show high tensile strength and rigidity, improve EMI shielding, and steady electricity dissipation, and reduce the friction coefficient against the steel. And therefore, PPS or their composite has been used for many applications such as electrical engineering part, and connectors, coil formers, bobbins, and thermal blocks, motor housings, and switch components. Also can be used for mechanical engineering part, gear pumps and gas valves, carburetor parts, and ignition plates, and flow control valves for heating systems. And also, they are used for cooking appliances, sterilizable medical, dental, and general laboratory equipment, and hair dryer components. Now, this is the last subject of this lecture, polyamides. Polyamides are condensation polymers composed of organic residues linked via cyclic imide groups. What is a cyclic imide group is? CO, NHCO. This group is called imide group. Imide group is cyclized here, and then this group is called cyclic imide groups. These cyclic imide groups are generally synthesized from reaction between organic diamines and organic tetracarboxylic acid. Polyamides has many excellent properties. They show the exceptional heat resistance, the excellent mechanical properties, high softening temperatures, excellent electrical properties, good solvent resistance, good flame resistance. So this is the general chemical structure of polyimide. Here R prime could be aliphatic or aromatic. Here R must be cycloaliphatic or aromatic. So polyimides can be synthesized from polyamic acid precursors. In other words, the classical synthetic methods to prepare polyimides is a two-step process. In the first step, the anhydride is reacted with diamines to produce polyamic acid here. This is amide group. This is the carboxylic acid group. This group is called amic acid. This polyamic acid is soluble, and therefore this is processable. And then if you further increase the reaction temperatures, this amic acid is cyclized to form imide group. This is a polyimide. Now this polyimide is not soluble in any solvent. Polyimide does not melt. And so of course you cannot process polyimide anymore. So in order to process polyimide, first you must use polyamic acid solutions. For example, if you make polyimide films, first you prepare polyamic acid, which is soluble in dimethyl acetamide, DMF, or NMP. This solution is cast on the plate, and then you evaporate the solvent by heating. At the same time, this amic acid is cyclized to form polyimide. Right? So after cyclizations, you are never able to process anymore. And this is the general schemes, more typical scheme of a synthesis of polyimide. This one is 4,4-oxydianiline is reacted with pyrometallic dianhydride in a solvent of dimethyl acetamide to produce this polyamic acid. This is amide group linked to meta positions, this is para positions. Right? Now if you further increase reaction temperatures up to 300 degrees centigrade, and then these amic groups, the acid group is cyclized to form imide group. This is polyimide. So another method to prepare to synthesize polyimide is to use amide-imide exchange reactions. This is already polyimide, right? Cyclic polyimide. This imide is reacted with these diamines. These two mixtures are refluxed in NMP solutions, and to form this amic amide here. And then if you further increase the reaction temperatures up to 300 degrees centigrade, this amic amide is cyclized to form amide groups. This is a polyamide. This is another pathway to prepare polyimide. In these cases, the ammonia is removed here. So in this case, this is water is removed, but in this the amide-imide exchange reactions, ammonia gas is evolved. So this application on polyimides is very wide. Particularly, polyimides can be used for jet engines. Right? In the jet engines, wheel pairs and strips, thrust washers, bushings, and bearings, bumpers, seals, and valve seat are made of polyimides. Also, polyimides can be used for electronics and information technology. So integrated circuit, for example, this is the circuit is printed onto polyimide film. This is the integrated circuit, and calculators and cameras, displays, printers and computers, and the flop disks, and this is tapes. So all of these, the applications is successful when you use polyimides. Okay. So this is the end of lectures. Thank you very much for your attention.